All right, so we are recording. Today we're going to go over the exam two. We are going to have our exam two next Wednesday. Okay, because I always have the actual exam, two classes from the review of the one from the previous semester. Because next Monday is a holiday, so that's why today we have class. We'll talk about the exam, and then on this Wednesday, that's the only chance of asking questions in a lecture. And then next Wednesday, because next Monday is a holiday, so next Wednesday, we are going to have our own exam too. Do we have any questions about when we are going to have our exam too? Okay, so next Wednesday. So what we'll do today is to take a look at exam two. And I shared with you exam two from before because the floating point question was from exam two. That was question number 3 out of the 3 questions. But the other 2 questions are relevant for our exam two at this point. So the PDF is right here. You're more than welcome to open it up on your side so that you can jot down notes if you want to. So I'm gonna open this up, or at least download it on this side, and then I'm gonna open it up. All right. So let me see if I can minimize this portion. Where's the okay? There we go. Magnify, magnify, magnify. All right. So in terms of the what material you can bring with you, it is very similar to last time. You can bring anything that is on paper, so that can be your own notes. It can be my modules. You can print out all of those if you want to. Any sample program that we talk about in class, you can include those as well. In fact, anything that is either printed or handwritten on paper, you can bring it with you in exam two. But no electronic devices, so that means no tablets, no cell phones, no laptop computers, and so on, during the exam. So do we have any questions about what is allowed and what is not allowed? No questions? All right. So you can also bring a calculator with you. So if you want to bring a calculator, even the graphing calculator, you can bring that. I do not think it is going to be particularly helpful, but if you want to bring a calculator just in case, that's perfectly okay. All right. I will not be providing you with the processor. Okay, so that means if you think the diagram of the processor or the ALU or the register bank will be helpful, you need to bring your own. Okay, so that means if you want to bring, you can bring a whole stack if you want to, just in case you think, okay, I'm gonna mark it up and turn it in as part of my answer, but I might get it wrong the first time and I'm gonna redo it. So you can do that as well. But other than that, it's basically the same, as the first exam. So we're going to go into this part here and start to look into the first question. So be sure to read the entire question because in past semesters, I would be trying to do all my own questions and then read it incorrectly and then end up with the incorrect answer. So read it carefully. The circuit to analyze in question number 1 is represented in text as follows. So this is the truth table for the SR latch. Now, is this the same SR latch that we have been talking about in this class? Maybe, maybe not. Okay, but the truth table is included as a part of the question. So pay attention to that because it may or may not be exactly the same as the SR latches that we have been using. Now, in this case, is it the same? Well, let's see. If both S and R are zeros, both Q and NQ are ones, okay, that seems consistent. If S is 0, R is 1, then Q is a 1 and NQ is a 0. That seems consistent as well. If S is a 1, R is a 0, Q is a 0, NQ is a 1, that seems consistent. So as far as I can tell, this seems to be consistent with the SR latches that we have been talking about in this class. The comments here are also incorrect. So in this case, this is my fault. These are incorrect. This is a AND gate. This is a SR latch as described here. and these are input pins. Okay, B and G are input pins, and H is an output pin. All right, so do we have any questions leading up to this point? If I messed up, like having inconsistent things, like it's declared as an AND gate, and I'm commented as an OR gate, come to me. Okay, tell me about. Okay, I'm not really sure because the comment is inconsistent with the actual code. All right, so in this case, the circuit has 5 steps. Okay, so the first step is B and G both being 0. Step 1 is B and G, 1 is a 0, maintaining as a 0. Then G transitions to a 1, and then the next time, G transitions back to 0 again, and then B transitions to a 1, and then G transitions back into a 1 as well after that. So that's the whole sequence. And you guys may be thinking, oh, we won't have enough time to do all this. Well, the nice thing is I'm giving you a table that is mostly filled up already. So your job is to fill up the portions that is blank. So in this case, every row is either filled or not filled at all. So that means in this case, this PD row and this NC row, I think they need to be filled in. This NC row and this PD row, they probably need to be filled in. PD, NC right here, and also okay, we'll just go ahead and read the question and kind of be sure about what this is asking. An NCPD trace is already done as presented below, but however, some columns, okay, so we're missing columns, not missing rows. Each step consists of NCPD phases. NC updates only when input ports of devices or ports of output pins is based on. So this is a description that is consistent with your PD and your NCPD lab activity. So if you're not really sure, how to follow that instruction, you can revisit that particular lab activity. In addition, at the beginning of each step, a change input pin will be indicated on the initial NC row of the step. PD is potentially updating output ports of devices based on the changes of input ports of the immediately preceding NC row. If the value of an output port remains the same despite the update of at least one of the input ports, leave the corresponding cell blank. In other words, if there's no change, you leave the cell blank compared to what it used to be. Okay, is that okay? Do we have any questions leading up to this point? Okay, all right. A step terminates if and only if no node is affected, indicating there are no changes to any input port of any device. The end of each step becomes the beginning of the next step. Each step should start with NC and end with PD. Assume all ports to be unknown initially. So that is already indicated by the trace itself. In the last phase of each step, PD does not result in the change of any input port of any component. Complete the following table to specify the phases by filling in the missing values of certain columns. The header of each column identifies the node ID, the device as a letter, and also the port. So this is consistent with how this was done in the lab homework, not the homework, but in the lab activity that we did. So if you see a particular column having values, that means it is not something that you have to work out. On the other hand, if you see something that has a column that is missing a lot of values or missing values entirely, that means that is a column that you need to work on. All right. So do we have any questions at this point? Oh yeah. Oh yeah, definitely. That's what I'm trying to test. So we can see that this column is empty. There are no values filled whatsoever. So is this column here, and so is the column right next to it. And then there is one column here that is also missing all the values. There's another column here, and also another column over here. Okay. So the first thing you need to do is to identify which columns are missing values so that you know what to work on. All right, so the way I'm going to work on this is to assume that I have to work from the beginning. So the first step here, okay, I have to go back and forth, unfortunately. The first step is B and G being 0. So that's the starting point. So that starts with an NC and node connectivity. We have B, um, G both being zeros. So these are the two that have zeros to start off with. And then because this is belonging to node 0, so everything on node 0 should automatically get a 0. So that explains this 0 here. This is on node 1, so everything on node 1 should also get a 0. And this is on node 1, and so is this one. They're both on node 1. So that explains the N0. It is all done correctly. The next one is a PD, which means we look at devices where the input, at least one input port has changed. Now, before this row, everything was unknown to begin with. So any transition from unknown to a 0 is a transition, that is a change. So now we have to look at the input ports. Is R of device J an input port? Okay, what kind of device would have an input port called R? Okay, what kind of devices did we use in this particular circuit? Yep, SR latch. The R of the SR latch is the name of one of the input ports. So this is an input port, which also means the SR latch potentially can update. I'm not really sure. Okay, so let's decide whether we know whether the output of SR latch J is going to be at least partially determined. Okay, in other words, just knowing that one of the input pins or input ports is now a 0, do we know, can we confirm the state of at least one of the output ports, which were all unknown to begin with? In other words, can we fill in any one of these two? Okay, so how do we solve this problem? What is your process? The truth table, very good. Okay, so we look at the truth table. We say, okay, we know the R port is a 0. Can we determine any one of the output ports? So if you go back to the truth table, okay, right here, the R is a 0. Okay, this row has R being a 0. This row also has R being a 0. You go like, well, we can't really say anything about Q because in one case Q is a 1, in the other case Q is a 0. So we cannot say anything about Q because we don't know what S is. On the other hand, NQ is both, in both cases, are 1s. So we can now say, oh, okay, knowing that R is a 0, we now can confirm that NQ has to be a 1. It is deterministic. So that means we can now go back to the table and start to fill that in. I am not sure I can actually edit this one here. So let me see if I can. It's already downloaded, I think, but I'm going to download it anyway. Yep, it's already downloaded. Okay, so what I'll do is I have to open it and with my own tool. There we go. Okay. So this tool does allow me to kind of write over. So I'm going to use a text tool to write over the cell that we know what the value has to be, which is this one here. NQ has to be a 1. So I use the text tool and I'm not sure what is the right size. We'll give it a try. 1. Yeah, close enough. Okay. So does everybody understand why I put a 1 over here? Oh, it should be the one above. Yeah, you're correct. So let me move that. Nope, not this one. Oh, the other. This one here. There we go. That looks good. Okay. So does everybody understand why I can put a 1, where I put it? Let me highlight it, because that makes it a little bit easier to read what is changed. This is the one that I'm talking about. Okay. So what else is getting, potentially getting an output that we know for sure? F, but F already has that one already pre-filled, so that's that one I don't have to deal with. This is one of the inputs of device A, and device A is an AND gate. So do we know the output of device A just knowing that one of its input ports is a 0? It's going to be a 0. Very good. Okay, so we put another one over here. I'm just going to use the pencil tool. I think it's actually easier for me to just kind of handwrite a 1 here. Is that okay? Does everybody understand why or what reason I use to put a 1 here? Because device A is an AND gate, a regular AND gate. So if one, oh, it should be a 0, not a 1. Sorry, I take it back. That was my bad. My bad. Okay, let me erase it. So I should put a 0 here. Right. There we go. The placement of the object, sometimes is off. So it's kind of need to put it here. There we go. So that's a 0. So these are the two that I added, which also means if you use a pen that is not black, it will stand out a little bit better. It's easier for you to track all the things that you have done. All right. So this is node 4. And next NC, I'm expecting all the node 4 to also change to a 1, which is this one here. And that's the only other node 4. So let's go ahead and change that. All right. So I'm going to use the text tool. Put a 1 over here. Okay. And then the other one is node 2. So all the node 2 also need to change to a 0. So that would be this particular 0 over here. And I'm going to highlight both of those just so that we can tell that these are the updates. Okay, so there's one here and there's also one here. Are we still doing okay so far? Yep. What are the places for J's F and G? Say again? The base part of J's F. You mean how the input pins are changed? J, F, letters. They're all up here. Oh. Yep. Yep. So the whole circuit is described up there. But since we only have an AND gate, that's not an SR latch, so everybody else are just SR latches. And that's why I don't even have to refer to here to know what kind of devices I'm dealing with, because either it's just an input port or output port, or it is an SR latch or an AND gate. All right, so now we have NC. So as long as the NC is not, it's not blank, the next row, you need to figure out the PD. So with this one, we have both S and R being zeros at this point. So the output is a 1, that is correct. NQ is already a 1, so that's also correct. The next one is this one. We changed the S port to a 1. And as a result, the Q port is going to be a 0 in this case, because we have 1 and 0 as the S and the R. So the output has to be a 0 and a 1 as Q and NQ. So that part is done correctly. And the next device that has at least one of its input port changed is SR latch D. But SR latch D is only having the S pin being a 1. The R pin is unknown, so I cannot make any conclusion. And that's why this column here cannot be filled in at this point. It is okay to be blank at this point. The next column is actually computer filled in already, so I don't really have to fill that in. But if I even need to fill that in, it would still be a blank, because just knowing one of the input port out of the S and the R is a 1, but not knowing the other one. Well, actually, we know both of them, 1 and 1. But even with both of the S and the R input port being ones, we still cannot know what the output ports are. Yes, you're just trying to go up. Okay. Oh, we're still on the first step. We're still on step zero. The truth table. The actual table. Oh, okay. Yes. So the input would be B and G both being zeros. That's the first step. The steps were described in the previous page right here. We are still on step zero. So B input pin B and input pin G are both zeros at this point. Is that okay? I mean, do you the spreadsheet? You mean here, the actual table? Those are the node numbers. Oh, okay, all right. Yep, so those are just the node numbers. So now we are up to the next PD, or I just explained the next PD. So we were working on the Q and the NQ, these two cells, and they both should be unknown at this point because we are doing an NC, because when both input pins of an SR latch are ones, the outputs are NC, but in that case, the NC means not no change. Well, no change from what? No change from unknown. So that means I still don't know what they're supposed to be, and that's why they are left blank at this point. So that's why these two cells are still blank. Let's take a look at this one here. This is the other input pin of the AND gate of A. But since one of the input pins of the AND gate is still a zero, it doesn't matter if this one turns into a one. It won't change the output from a zero to a one. So the zero stays, which means we don't put a value in that particular cell. And then the other three over here, they're all ports, which means they don't um, change out of a PD. They change outside. They change because of an NC. All right, so this row is all done, and the next NC, okay, we have to be careful because this is a change of port node 5. So node 5 is changed. This node 5 gets a 1, so that is correct. This is a node. This one does not have a node number, so it can change all at once, and nobody else is going to update after an NC in this case because this particular output port of the SR latch is not connected to anything else. So NC is not going to affect anything after this. So after this, we have this pin turning into a 1, and we have 1, 1, and then the output would be unknown at this point. Okay, so that's okay. So that's why this entire PD row is empty, which means it is the end of step 0. So now we are moving on to step 1. Step 1 is changing G from a 0 to a 1. So that means everything that connects to node 1 also need to change to a 1. This is a node 1, it changes to a 1. This is also node 1, it changes to a 1. There are no additional node 1s, so that means this NC row is in fact done. So the next stage is to look at all the devices where at least one of the input ports have changed. So we look at this one here because it just got changed from a 0 to a 1. So now we ask, with device F, is the output going to change? Well, if you look at device F, its inputs are both 1 and 1 at this point. So when S and R are both 1s, we have no change to the output. So that means these two cells being empty is correct. So that's fine. This is the second input pin of an AND gate. It changed from a 0 to a 1. So now both inputs of the AND gates are 1s. So that means the output of the AND gate needs to change from a 0 to a 1. So there is a change now to the output of the A device or the AND gate. So it's going to change from a 0 to a 1. And I will highlight it as well, just so that you can see what changes, what I wrote, in this particular document. But that's the only thing that is changing in this particular PD or propagational delay, step or phase. And now we are going to NC again. This one belongs to node 2, so all the node 2 needs to change to this one in the next NC. This is the only other node 2, so that one also needs to change to a 1. So I'm going to put a 1 over here. Okay, I'm going to highlight it too so you can see it. There we go. All right. So this is one of the input ports of an SR latch. So as far as this particular SR latch J is concerned, we now have 1, 0 as its input. So the output is going to change accordingly. The only change is the Q port being changed to a 0, which is already filled in the original table. But you can basically see what columns you need to actually fill in. Okay, and most of the columns are already filled. So the way I'm working on this is I'm explaining every single value, okay, because I think that might be helpful for review purposes. But when you are doing this, if a column already has a value in this particular test, then you don't have to worry about that particular column. All right, so this is a 1, and then the other one, it's a 0 here. This one is preserved because of the truth table of an SR latch. So that part is done. And since we do have one of the output ports changed, so that means we have another NC. The NC is propagating that change from a node 5 to everything else on also the node 5. This is the only other column that is node 5. So that's why we put a 0 here. So this part, the whatever table is provided to you is already done. So because this 0 is a R input of SR latch D, so SR latch D now has 1 as is, okay, let's see, as the S input is a 1, and then the R input is a 0. So now the output also has to change accordingly, because now NQ is confirmed to be a 1 when Q is supposed to be what? It should also be a 0 for Q. So now we have to make a note of that. Put a 0 here and then highlight it like so. All right. So are we still doing okay so far, in terms of what you need to do? Okay, all right. So moving on, it gets a little bit more difficult to track, because this is going to scroll off the screen at some point. But, at least at this point, we're still okay. So the NC has to propagate those changes. And we do have 2 nodes being changed. I think I put the 0 in the wrong place. Okay. I have to step over here to make the alignment right. This is Q, this is NQ. Okay, that is correct. Okay. So this 0, which is changed from unknown, is on node 6. So now I have to update all the node 6 to a 0. Scanning across, this is the only one that is also a node 6. So now this thing has to change to a 0 as a result. There we go. Put the 0 here and then highlight it. This one does not cause any update because this one belongs to an output or output port that does not connect to anything else. So there's nothing else that's going to be affected by this change over here. This one is not the input port of a device because it's just an output pin. So we are now done. The next PD row is empty. There's none of the devices would change its output as a result. So this is the next phase here, which is NC being turned from a 1 back to a 0. This is a node 1. So these node 1s are changing accordingly. So to follow a table like this, it might be handy for you to bring a ruler with you so they can kind of more properly align, the columns. So it's easier for you to kind of see which column you're referring to. Because I'm having a problem keeping track, because I have to do it, you know, kind of remotely. Doing this on paper is actually a little bit easier. All right, so we are moving on to here. So these are the inputs. So now we want to see if device F is going to change. So device F is a SR latch. So at this point, we have 1, 0 as its input. So the output should be a 0, 1, which they are already. So none of the output is going to change over here. So they should remain blank. We now look at this particular 0, and this is a 0 as one of the input pins of an AND gate. That AND gate had an output of 1 before, and that has to be changed to a 1 now, because with an AND gate, if at least one input is a 0, the output needs to be a 0. So we put a 0 here. I can probably change the text color so I don't have to go back and keep highlighting things like this. All right. But that's the only change. This belongs to node 2. So now I have to follow all the node 2. And I'm going to change now and use a kind of blue pen. Not sure how it shows on the screen, but we'll give it a try. This is the only other node 2. It is also going to change to a 0 at this point. Like so. Does the color blue show up okay, or do you guys prefer me to also highlight it? I'm going to guess you want me to highlight it. All right. So, so now this particular SR latch has 0, 0 as its input. So the output should both be ones, which means this output should become a 1. And that's exactly what that is doing. Okay. And now we scroll the header out of the screen. So I got a little trick here that can still help, because I can take a screenshot of just this portion and then put it into a viewer. So this way, I can put my viewer kind of aligned with the columns. So this way I can scroll things up and we can still have a view of the column headers. There we go. Okay. All right, so this is the last update, and then with right. So this belongs to node 5. So all the node 5 needs to change. This is the other node 5. It becomes a 1. And now we have to look at SR latch D, because I scroll. This is the difficulty is I have to look at the S pin too. So we have a S pin being a 1 and R pin being a 1 as well. So when you have both R and S being 1s, it preserves the value. So the output do not change. So being blank here is fine. So now we have another PD row of being all zeros. This is step 2. So step 2 is having B as an input pin being changed from a 0 to a 1. So that means all the node zeros have to change to a 1. This is the other node, this is the only other thing connected to node 0, so it is also changed to a 1. So now SR latch J has 0, 1 as input, so the output becomes 1 and 0. So let me scroll up and see if that is a 0. Nope, it is not a 0. So that means it needs to change to a 0 at this point. Okay, so that means this cell needs to change to a 0. I'm going to highlight it first and then go back and change the value to a 0. Here we go, the 0 here. All right. So that's the only output pin that is changed. It belongs to node 4, so all the node 4 needs to change now. This is a node 4, so that needs to change to a 0. And we don't see any other node 4, so that's the only change we need to do. Now this is the S pin of SR latch F. So if that is changed to a 0, now we have 0, 0 as the input of SR latch F. So that means both of the output of the same SR latch needs to change to a 1. So that's why okay, I need to align again. This is S, this is R. So both of the outputs should be 1s. So that's why this is changed to a 1. The other one is probably a 1 already. Let me just double check. Nope, the other one is a... Oh, that's a 1 already. So we're looking at the NQ port of F. It is already a 1. So the only change we need to do here is this one here, which is the Q port of device F. But it does not connect to anything because this particular node or this particular output port does not connect to a node. So that means nothing else is going to update because of this change here. So the next NC row is, or am I misreading? No. Okay. Yep. So that's the end of this particular step. This is the next step here, where G is becoming a 1. It's transitioning from a 0 to a 1. So we are basically going through the same thing all over again. So I can kind of short circuit the analysis at this point because we already know which columns we're interested in. It would be this one, this one, this one, and there are only a few columns that we need to pay attention to. So we just have to look at those particular columns. So this column is one of those. So when the device D has S being a 0, then Q of the same device also needs to turn into a 1. So this cell needs to turn into a 1. Highlight this. And then in the next NC step, this 1 also needs to propagate to everything that is on node 6. So that would be this one on node 6. That also needs to turn into a 1. Like so. I believe that is it, okay? Because if you look at all the columns that we actually have to update, these are the ones that need to update, and no one else should be affected because of the other cells that are already filled in. All right, so do we have any questions about how to answer this particular question? Okay, I'm taking this as you don't have any questions? We good? Okay, all right. So we are now moving on. Let me take this one out. And we're moving on to the second question. So the second question is basically testing, do you understand how things connect inside the processor? So for this question, it will be helpful to bring a map of the processor itself, the ALU, and also the register bank. I already provided the PDF that you guys can print out in order to kind of have your own maps of what is inside the processor. So that would be super helpful in this case. So observe the following RTL description. Whatever C is pointing to in RAM is updated to register A. So the part 1 of the question is describe the port connectivity needed to implement the RTL description. This can be in the form of assignments where the left-hand side is the input port and the right-hand side is the output port. For example, the fetch operation can be described correctly as this. So this part here is the description of the fetch cycle. So now the question is, how do we describe this using RTL? So now you have to think about the devices. where they can be active, they can be doing something. So those would be the four registers: RAM, the instruction register, the program counter. So those are the things they can serve as endpoints. They can either provide a value for somebody else, or they can update to a certain value that somebody else has already provided. Are we doing okay so far in terms of identifying what components can be a part of this answer? Okay, so I have already mentioned it. You might need to write down in your notes. Okay, it's the same kind of analysis that we have already talked about. What devices can provide a value, what devices can update to a particular value. All right, so in this case, register A is on the right-hand side of the assignment, which means it is providing a value. Okay, so that means we can now say something is on this side, and then the Q port of A is providing a value to update whatever the question marks are representing. So now the question is, what are the question marks representing in this case? In other words, how do I say the memory location that register C is pointing to? Well, I mean, there are a few things. So in this case, whatever A is outputting has to go to RAM dot D, because the D port of RAM is the port that it receives the value so that it can update one of its locations. But this is not the only thing we have to express. The other thing we also have to express is where are we updating? The A part of RAM dictates which location is being updated. So we need to go like, okay, so who is telling me what location is getting updated? Can somebody answer that question? From the RTL, and also from what you know about the dereference operator in CISP 360, can you tell me what has to specify the value of the A port of RAM in order to say, hey, this location is the one that is getting updated? Yes? It would be C.Q. That is correct. So the correct answer to this part of the question would be these two lines, okay, these two so-called assignment operations, because they are basically saying these are the endpoints. A.Q is an endpoint to specify a value. RAM.D is an endpoint to receive that value. And then the same thing with C.Q, it is also an endpoint to provide a value. And then RAM.A is another endpoint to get a value. Okay, so are we doing okay so far with this part? Okay, so now we move on to the second part. For each line of the previous part, list all the relevant tunnels to contribute to the routing from the output to the input. The ordering of this list is not important. This list is limited to tunnels at the top level of the processor. There's no need to specify names that are internal to the register bank or the ALU. Okay, so this is giving you an example. If I need to specify that RAM.D needs to connect to instruction register.D, then these are the tunnels that are involved in that particular route. If I need to specify that RAM.A is connected to PC.Q, then ALUOP and RIEN are both involved in that particular determination. I think this is not supposed to be ALUOP. The answer is not supposed to be right, okay? I'm just giving you an example of what it should look like. All right, so now we know that we need to route these things together. So the question is, can you tell me what needs to be configured along that path in order for these two things to be connected? How do we answer this question? I cannot answer this question without a map of the processor. So if I cannot do it, I think you might want to bring a map with you in order to answer this kind of question. So let's go ahead and open up either Logisim. I can do Logisim in the class, but in the exam you cannot use Logisim. But I'm not going to use LogicSim in an interactive way. I'm only using it, just to display a map so that I can point out, what tunnel will be involved. So let me go to processor 0004. All right. So we'll go back to the spreadsheet or the answer sheet here. We'll answer one thing at a time. So we are going to answer the first part first, which is ram.d needs to connect to a.q. So how do we finish that routing? You can start with the input, you can start with the output. That is entirely up to you to decide which end you want to start first. But generally speaking, it is good to be systematic in this way. So I'm going to be, I will start with the input, which is ram.d. This is ram.d here. So it routes all the way to various things, but eventually I need to route it to a.d, which is coming from the inside the ALU. So now we have to go like, okay, so which one is it going to connect to? So this wire connects to this wire, and then this wire goes across. I mean, if I zoom out a little bit, I think that actually helps. All right, so we are looking at this wire here, and it can go all the way here. But this is already serving as the input into the register bank, which is not what I'm looking for. So let's look at another way, which is coming out of this multiplexer. Okay, so this demultiplexer seems to be important. So that means in order to finish that routing, register output 0 has to be enabled, and then register 0 demux has to be a, okay, I'm going to write this down on a piece of paper because, when I'm talking and trying to figure this out at the same time, I can't really do that. So register output 0 enable needs to be a 1, and then register output 0 demux needs to be a what? I'm asking about this tunnel. This tunnel needs to be of a particular value. What value does it need to be? 0. Is it 0? 0, 1, right? I don't think it is supposed to be 0, 0 in this case, because this is the output that connects ultimately to the D port, which is over here, and that would be output. 1, 0 is correct. Okay, it's output 2, but so in binary it is 1, 0. Okay. All right, and that is coming out of output 0, and the register that we use to select which register is connected to output 0 is coming from register output select. So that means register output 0 select needs to select register A, I believe. Okay, let me just double check. Yep, it is register A. So that would be 0, 0, because we use 0, 0 to specify register A. I'm talking about this particular tunnel here. Register output 0 select has to be 0, 0 in order to specify the output of register A inside the register bank becomes output 0 of the register bank itself. Okay, so that part, okay, depends on how well you understand what is inside the register bank. Because ultimately, what we really want is for this to go here. But in order to specify input 0 to connect to register output 0, it means our register output 0 select needs to be 0, 0. So that's what I was referring to earlier. All right, so I think that finishes the routing, that routing of the first part here. So in this case, this part 2 does not need to know the value. It just needs to know, what are the tunnels, what tunnels are involved in this process. So if I were to just comment on the tunnel, the name of the tunnels, it'll be register output 0 enable, register output 0 demultiplexer, register output 0 select. The specific value is specified in the table, in the next step. But I got one more step to go here because I also need to. I'm also I also need to know how RAM.A and C.Q are connected. So now we basically go through the same exercise, except this time we track down a different wire. We track down this wire. Okay, it goes to here to a multiplexer. So now we have a choice. We can either specify input 1 go to output the output, or we can specify input 0 to go to the output. In this case, it is output 0. So I'm going to have to write this down on a piece of paper. ADDR mux needs to be a 0 in this case. So input 0, if I follow the trace here, ends up here. So that means this particular demultiplexer also needs to be specified. So that would be register output 1 demux. And that needs to be which value? I need to connect this wire, okay? I'm not clicking on it so that I cannot cheat with having the wire highlighted. So I'm still using just my eyeball to follow it. This is output 0, so that means this select also should be a 0. So register output 1 demux needs to be a 0. And that's coming out of output 1 of the register bank, and register output 1 select is telling me which register, the output of which register connects to register to output 1. So in this case, we need register C, so that means it needs to be 0. So register output 1 select needs to be a 1, 0. Okay. So I think those are the only signals or tunnels that I need in this case. So if I were to comment here, it's going to be ADDR mux is involved, register output 1 DMX demux is involved, register output 1 select is also involved. So that answers the part 2 of this particular question. Do we have any questions about what I'm asking and how I figure that out? No questions? Okay. But you can probably tell that, I cannot answer these questions without the map because I cannot remember the names of the tunnels either. So that means, you probably need to bring, the map. You can also pre-color code things if you want to. Okay, if you think that's going to be helpful, you can pre-color code the register bank, the RAM, the registers and so on, so that that gives you like places to focus on when you're trying to answer questions like this. All right, so the next step is use the provided table to describe the following for each row, the following for each row. So the signal is the name that is provided. The value is what you need to specify. So for the ones that you do not need a particular value, you can always specify a question mark and say, that one we don't care. And then you have to explain a reason here. So I'm not going to write down the reason, but I will write down the value. All right, so for every single row, we have to answer the question. The first one is a little bit kind of difficult because we are asking, what about bit 0 of the output of ROM? Well, in that case, you kind of have to look at the map and try to figure that out. This is this is the output of the ROM, the D port. This is bit 0 of the output, and it is going to instruction register, the enable of the instruction register. So are we updating the instruction register with the description that we are talking about? Nope. Okay. So that means it has to be a 0. Okay. In this case, it is a 0 because we do not intend to update the instruction register. So if I were to write down a very short answer here, we'll just say that the instruction register is not being updated in this case. All right, RAM cell. I can go back to the diagram, but what do you think? RAM cell, which is the select port of RAM, should it be a 1 or 0 or a question mark? It should be a 1 because we are updating a location in RAM, so the RAM component better pay attention. RAM load needs to be a 0 because we are writing to RAM. So as a result, this needs to be a 0. RI mux is going to be not care, okay, because we are not updating any of the registers. So this one is going to be a not care or question mark. RIEN is going to be a 0 because we are not updating any of the registers. So this one has to be a 0. If it is a 1, it means at least one of the registers is going to be updated to something, which is not what the RTL is describing. Okay, I'm going to change the font size a little bit. This one is a little bit too big, so I'm going to have to, otherwise I cannot fit the text into the space that I have provided here. So RISEL is going to be question mark and question mark. The reason why it has 2 question marks instead of 1 is the width of the tunnel needs to be reflected in your answer. RI cell has 2 bits because we use 2 bits to select one of the 4 registers. So both of those bits should be unknown in this case. RI register output 0 enable, we just talked about that. That needs to be a 1. And I'm just reading my notes here that I talked a little bit earlier. The select of that one needs to be 0, 0 because we're using register A to feed to the data port. And then the demux also needs a particular value. I believe it was 1, 0. Yep, that has to be 1, 0. Register output 1 select is going to be a 0, 0 because register, nope, I take it back. This is 1, 0 because register C is connecting to the address port. So that's why this has to be a 1, 0. From what we worked out earlier, register output 1 demux needs to be a 0, single digit 0, because that demultiplexer only has 2 outputs. So we only have to select one of the 2 outputs. The ALU is not in use in this case, so it should be disabled. If the ALU is already disabled, what operation we specify here should not matter, but that should be like 3 question marks because there are 3 bits to ALU OP, the operation select. Address mux is going to be 0. We worked that out a little bit earlier. PC mux is only useful if you're updating the program counter, which we are not doing in this case. So there are 3 question marks here. PCEN should also be a 0 because we are not updating the program counter. And then rom.d24 and 25, those are unnamed, so we just have to follow these. This is 25. 25 is going through the OR gate to basically cause the microcode pointer to reset. We are not ready for that, okay? So that needs to be a 0. And then bit 25, which is the very last bit here. Oh, I take it back. Okay. This needs to be a 0. And then we go back here and change this one because I messed this one up. Sorry about that. Okay. So the last bit, the second to the last bit is this bit 24. So bit 24 is going into this multiplexer. Right after the location of ROM that specifies what we need to do, we need to increment the microcode pointer. To increment the microcode pointer, that means this needs to be a 1. So that means when we go back here, this also needs to be a 1. So do we have any questions about how I filled up this particular table? So to do this part, you really need to know, how the processor works. Okay, what components are involved in the RTI that is described earlier, and if the component is not supposed to update, you have to make sure that it does not update, because we don't want to accidentally update something when it's not supposed to be updated. And then for certain things, if, for instance, okay, if the processor is not going to update, or if the PC, the program counter, is not going to be updated, then whatever you specify as PC mux really does not matter, because it's not mux, PC mux does not matter, because whatever it is not going to change anything. Are we doing okay so far with this part of the question? Okay. All right. So these are the only two questions that are relevant because the next one, question number 3, is a floating point number kind of question, which we already have experienced in exam 1. So we are not going to repeat that unless you guys want to. If you guys are all going like, I want another floating point number calculation kind of question, we can throw another one in. Okay, but that is not going to preclude the next kind of question because because of the reordering of the topic, I do not have the same kind of question from last semester. I can now close this window because it's not useful anymore. So this goes back to the let me close this too. I think oh, there we go. Okay. So this goes back to the last attachment that I sent in the announcement. The potential question type in exam 2. It is, I mean, for this class, it looks like a zip file. So I'm just going to go to my text window here so that I can show you what is inside the text file or what is inside the zip file. And there are two files. One is called findmin3.c, which is the C code, and the other one is TTP-ASM. So that's not how I intend it to be. So give me a second because I wanted to open side by side, not top down. Okay, so uppercase O, so open it side by side. There we go. The C code is on the left-hand side. The assembly code is on the right-hand side. So the C code is what we want to do. Okay, that is what we want to accomplish. The right hand, so the left-hand side is there's no problem that you need to fix on the left-hand side. It is reference. Okay, that basically tells us what we want to do. So the few things that are important here is the type of ABCD. They are unsigned 8-bit integers. Okay, and then the rest are really just another way to find the minimum given 3 variables A, B, C, and we want to store the minimum in D. And obviously in this case, A, B, C, and D are all registers because we haven't really talked about local variables yet in this class, so I can't use the concept of variables yet. On the right-hand side, on the other hand, we have a faulty implementation of the code. So VA, VB, VC are just labels so that I can load those values into registers A, B, and C for testing purposes. Okay, so if I want the same thing in the C code, I could have done it like this. So I would just say const u int 8_t VA equals to 2. Okay, so this is if I want the two versions of the code to be as close as possible, this is what I would have done. And then I just pre-initialize the variables like this. A equals to VA, B equals to VB, and then C equals to VC. Okay. Is that okay so far? Okay. I'm just backfilling the C code so that it is also consistent with the initialization code, so it looks exactly the same as the assembly code. Okay, so if we have extra instructions that really do not do anything, it's just sitting there, but it's not hurting anything, it's not causing the program to work incorrectly, we don't fix those. Okay, we just kind of leave them alone. It's like, okay, we don't really need the O up, no up here, but we'll just leave it alone. These 3 instructions are correct. Okay, LDI is the correct way to initialize a constant into a register. And then we move on to the compare instruction over here. Compare BA. So now the question is, if we are going to implement this part of the logic according to the way we break down the program to flatten the program, is this the way to do it? So let's see what this ends up doing. Okay, if we have a compare BA and then the JLI to else 0, one way to document this is to say, B, if B is less than A signed, then jump or go to label else 0. All right, so is that what we want to do? Sort of and sort of not, okay? Because when you look at the C code, it says if A is less than or equal to B and A is less than or equal to C, that's when we want to stay with the then statement. And if you refer back to the compiling code section, we basically look for the opposite reason to jump to the else case. So the question is, if B is less than A, is that a good reason to go to the else case? Okay, in other words, if B is less than A, okay, if B is less than A, which means if A is greater than B, is that a good reason to go to the else case? The answer is yes, but there's a problem. The problem is in the C code, A, B, C, D are unsigned. But in the assembly code, I'm using JLI. JLI is not the correct conditional branch. We should use JCI in this case because it is an unsigned comparison. So that means, okay, let me take it back here. So in your answer, you're going to have to kind of cross out the L and turn it into a C, or otherwise indicate that that is what we need to fix. But you also need to give me a short explanation of why you make that change. Okay, so I'm going to make that change here, and I'm just going to comment here and say C is for unsigned comparison. Okay, there we go. And then the same deal over here. Okay, you'll compare CA and branch if and only if um, C is less than A. That is a good reason. I mean, if A is less than or equal to B, but A is not less than or equal to C, we should still go to the else case here. So that means that's also a JCI to else 0. So this also needs to be changed to a C. C is for unsigned comparison, but otherwise the code is okay. Line 14 is easy to see that there's a problem because line 14 is corresponding to the then portion corresponding to line 12 of the C code. Okay, so we need to copy register A to register D. So we know that it is one of those things. Okay, it's one of the CPR, LD, or LD or ST. Okay, because only those three instructions would move things around involving the registers. But in this case, this is the wrong one because first of all, if it is an actual LD, you need parentheses around the second argument, the second operand. But LD is moving not between the registers. It's moving something from a location of RAM into a register, which is not what we want here because we don't see the asterisk operator here, which means we're not dereferencing. Okay, so this is the entirely wrong thing to do. So we need to change it to a CPR, copy register, which does not require parentheses, or it requires the lack of parentheses of both of the operands. So we basically have to say LD copies from RAM, CPR copies from a register, which is what we want. So that's a short explanation of what I fixed here. JMPI to end if 0. End if 0 is all the way down here, which means in the C code, once we are done with line 14 in the C code, we just go like, yeah, we are all done. Is that correct? Is that how we look at an else if kind of setup? Okay, if one of the branches fire, the statement executes, and then once that statement executes, then we exit the entire if else if structure. All right, so we are now moving on to here. So else 0 is corresponding to line 16 of the C code because technically C does not have the construct of else if. Okay, it has else and then a statement of the else. Okay, in other words, let me see if I can highlight it the way that I want to. In other words, from here, okay, from here all the way to here is a complete conditional statement that is technically nested in the statement that starts on line 12. So this is the correct interpretation in terms of the syntax of else if in C and C++. Some other languages has a construct called else if that is literally spelled as ELIF, else if. Okay, did I spell correctly? Nope. ELSIF. Okay, else if. But C actually does not have that, which means the highlighted portion here is technically a nested conditional statement that belongs to the branch of this particular else here. So that's why, in here, basically from here to the end is another conditional statement. So now this time we're comparing B and A. Okay, we compare B and A. And then this time we have the correct JCI. But the question is, are we going to else under the right condition? So what else is referring to is line 22. Line 22 is the else of the else. Because line 22 is the else of the if that starts on line 16. But the if starting on line 16 is actually the else of the if starting on line 12. So that's why I label line 22 as else. Is that okay? This has to do with parsing. How do we parse the structure of a nested conditional statement in C? Okay, I can see that there are a few looks here, okay, that suggests that we are not, it's not clear why it is called else. Does that help? That extra pair of braces are not needed, but I'm putting there here so that you can see how line 22 belongs to the else of the if that is starting on line 16. But that if is the actual else block corresponding to the if that is starting on line 12. Is that a little bit more clear? Hmm? That is correct, but that's also why in the assembly code, line 16 is simply else 0, because it is corresponding to the else of the outermost conditional statement. Yeah, but then I have to differentiate. I have to come up with a label name for this. I cannot just use another else because it is really a nested else of the other else. Yep. So that's why it's called else. But the question is this a good reason to go to this else? In other words, I'm really asking, when I do go to else, what is the relationship between B and A? This is saying if B is less than A unsigned, go to else. Okay, I'm just going to call else here instead of L0. So is that the right thing to do? Well, if you look at the C code, that is not the right thing to do. If B is less than A, I want to go to the then of the conditional statement. I don't want to skip over to the else. So that's actually the wrong thing to do. The compare is opposite to, the order of the operand is opposite. In other words, here, I actually need to fix this. It needs to be compare AB, okay, because I need to flip the operands so that we are branching only if A is less than B. A is less than, wait. We're comparing A, B. If B is less than A. Yep. So that's what we want is when A is, okay. Let me double check. If A is less than B, that's when we want to branch. Yep, that is correct. All right, so the operands have to be flipped even though the JCI instruction is actually correct. So over here is the same thing. because the way we want to branch is to say if B is less than or equal to C is false, then we want to go to the else over here. But if we want to specify B is not less than or equal to, it's the same thing as saying B is greater than C, or we are saying C is less than B. So the way to confirm C is less than B is to flip these two also. So C is less than B, then we go to else. So that means this also needs to be flipped. Okay. Then we get to this CPR. So line 21 of the assembly code is corresponding to line 18 of the C code. That is actually correct. Okay, not a problem with that one. CPR is the correct instruction to use. And then we have a JMP to else 0 and if 0. Well, what is wrong with line 22? First of all, having a branch over there is actually the correct thing to do. Because if you have an if-else statement, at the end of the then block, you have to go around the entire else block. So having this jump around the else block is the correct thing to do. But what is wrong with it? Why do you think the editor is highlighting the entire line and go like, this is not right? Nope, you just need an I here. Okay, what is the difference? Mm-hmm. And JMP requires a register. Okay, so one is using a register to copy over the program counter. That's JMP without the I. JMPI, on the other hand, requires a value that has to be a constant. A label is a constant. So that's why in this case, it is JMPI and not JMP. Okay. So now we go to else, which is corresponding to line 22. ST is the wrong instruction to use because ST is going to overwrite a location in RAM, which is not what line 22 of the C code is specifying. So this needs to be changed to a CPR. Okay, changed to CPR to update a register. There we go. Instead of what the register points to. So that basically concludes the entire program. The rest of the program is fine. This JMPI to end if 0 is not needed, but is it wrong to have it there? Nope, it's not wrong to have it there. It's just extra code that does not need to be there. So are we doing okay so far with this example of what you need to do? You have to spot all the problems with the code that is supposed to implement the provided C code. So you will be provided a chunk of C code, and your job is to figure out what is wrong in the assembly code and then fix it and give me an explanation. All right. We don't have a lab today because we have not covered parameters and return values, so we cannot have a lab today. But what you can do is to stay here if you want to, review the material that we just talked about, and then ask me questions during this time. Think of it as an extended office hour as far as this class is concerned. But at the same time, you're also free to go if this is lunchtime and you're hungry and go like, well, normally I cannot get my lunch this early. Well, today you can. All right, so that's the end of the lecture, and also a quick review of the questions for exam 2. Now, since we don't have a lab, let me just kind of ask you guys, if you guys want to leave, that's fine. How are you going to prepare for this exam? And you have a week and 2 days to prepare for the exam, which is a fairly good amount of time. The question is, how are you going to prepare? How do you study for a test where it is open book and open notes? What do you focus on? Practicing the lab can be helpful. Okay. So if you find one of the labs, where you cannot, go back and redo, let me know and I can kind of put it into the practice portion. I think most of them, are already there. You can just kind of practice as many times as you want. What else? There were some exercises that I mentioned earlier in the semester regarding, the processor. So what do you do with the processor? Let me bring up Logisim again, for that discussion. I need to go back to here. There we go. All right. Okay. So what do you do with the processor in order to answer some of the questions? You basically give yourself, some instruction like JCI L1, okay, whatever, wherever L1 is. And then you ask, okay, first of all, what does it do? If, what is the RTL of JCI to some label? Okay, you have to answer the question. So once you understand in RTL how it is described, then the next thing you need to do is to say, how does the processor get the job done? In other words, if you figure out that the program counter is going to be updated, then the next question is, who is providing that value to update the program counter? In this case, it's a location of RAM. So now then the next question that relates to some of the um, things that we did today is to say, okay, let me see. This is the output port of RAM, which is the D port of RAM when it's being read. This is the input of the program counter, which is also the D port, but this time of the program counter. How do I make a route from this port to this port over here? Oh, it has to go through this multiplexer, blah, blah, blah. Okay. So now you have to go like, okay, so how do I make sure that each multiplexer is selecting the correct input so that I eventually route the D port of RAM into the D port of the program counter? So some of those, multiplexers is coming from an AND gate. Some of those are coming from PC-MUX, but PC-MUX is not coming out of the ROM. So now you have to ask, so what is controlling the value of PC-MUX? Well, PC-MUX is the output of a multiplexer where the select of that multiplexer is PC-MUX-MUX. So now you have to ask, okay, so that particular multiplexer has 8 inputs. So now you ask, so which one of the 8 inputs should I select as the output to become PC-MUX? So those are the questions that you need to answer, when you are working out just a JCI instruction. Now, JCI is a little bit more tricky than other instructions because it is conditional. So depending on whether the carry flag is a 1 or a 0, the path varies a little bit. Okay, but that is also why the RTL corresponding to JCI is a ternary expression, because it depends on whether the carry flag is a 1 or 0. Okay, so that's something that I have recommended, for you guys to do, in the past. If you have not done that yet, you still have time, okay, because we still have more than a week before, this exam. But that's basically is what you need to do to each member of each family of the, well, okay, for each family of the instruction set, you probably want to pick one to work on. So if I were to go to the opcode table, I would say this by itself is an instruction. It is not conditional. These 5 is a family. They all work about the same way. Okay, the only difference is which flag do they look at. CPR is fairly simple. Okay, but you can also think of this and LD and also ST as one family of instructions, because all of these will either update or use a register to update something else. So in that sense, they are quote unquote in a family. LDI is kind of an oddball, okay, because LDI has some similarity to JMPI, but at the same time, it also has some similarity to LD. So it's hard to classify which family it belongs to. You can also think of it as its own. And then we have a whole bunch of stuff that goes through the ALU. We have add, subtract, right shift, logical not, I mean bitwise not, logical and, um, bitwise and then bitwise or, and also compare. These are basically all in the same family because they all have to do with using the ALU to perform some kind of operation. And as a result of that some kind of operation, it will also update at least two of the flags of the flags register. The Z flag and also the S flag are always going to be modified by these instructions. Now, whether the overflow flag is going to be modified, it kind of depends, okay? Because only the add, subtract, and compare instruction makes sense to modify the overflow. The L flag, on the other hand, is the result of, it's the exclusive OR between the overflow and the sign flag, which means every time you change the sign flag, you probably may end up, changing the L flag too. So these are all in one family. I am not going to quiz you on this particular family, which are basically all the jumps but without the I, okay? Because these are the ones that we introduce after we talk about calling and returning, which is out of the scope for this particular exam. But we also have increment and decrement. So these two we will also include it in the exam. They are very simple ones, okay? Basically we are incrementing or decrementing the value of a register, but they are tricky in the sense of how they do not change the flags, okay? So you have to kind of look into these two, okay, and say, how can these, basically do what they need to do without specifying the second operand? Because if you want to add one, if you use the add instruction, you always have to specify two registers. But these require no other register than the one that you want to change. So the question now is, where is that constant of 1 coming from? Okay, so that's question number 1. Question number 2 is all of the other things to use the ALU, they all change the flags, at least the Z and the S flag. This one does not. By design, this one does not change the flags. So the question is, why is it not changing the flag register? Okay, so you might want to ask that question. The answer to all of these questions are in the processor design itself. Okay, I know it looks like a mess. Okay, it is kind of complicated, but each component is something that you already understand. So the only thing you need to do is to make connections between all of these components and keeping in mind what we want to accomplish. Okay, so that's the key. So other than this, the PD, NC kind of thing is really a practice thing. Okay, you just have to kind of remember how that table works. I would say the last kind of question may be the most challenging, which is I give you a chunk of code. Okay, I give you like a C code. On one hand, I give you a faulty implementation of the C code on the other hand, and then you have to basically go like, okay, what is wrong with the assembly code? The best way to prepare for these questions is to understand how to quote unquote compile C code into assembly code. Okay, you do it step by step. Okay, because if you were me, you don't have to do it step by step. But if this is kind of like the first time you do something like this, do it step by step. Okay, the step by step instructions are in the module. So basically, you have to read that module and just look at this code here and ask, how do I translate this into basically flattened C code that has no structure in it, and all the conditions in the conditional statements are simple comparisons like less than or equal to. So you have to go through that process first. And then when you cannot reduce the C code any further, that's when you convert the code into assembly code. So if you go through that process a few times, you would probably get some experience of, oh, okay, now I understand, where to put what code or what instruction I should put here and so on. So that's all I can do right now. Okay, that's all I can say, as far as I know how to prepare for this test. Does anyone have any questions? Yep. Mm-hmm. Yep. Um, well, because in assembly code we can only check for less than, we can also check for equal to. Not in this case, because in this case, because we are looking for reasons to go to the else, right? So we are looking for A is less than or equal to B is false. But if A is less than or equal to B is false, it means B is less than A. So that's why we can convert not less than or equal to just less than. But if there are cases where you need to check for equal, then you need a JZI to catch the equal to. So you can have JCI, JZI kind of lumped together. One will take care of the case in case of a less than, and then the other one will take care of the case when it is equal to. And don't forget the trick that we did with the absolute value code, where we can use AND AA to basically to check the sign of register A in that particular case. But the same trick can also be used to see whether register A is 0 or not. So that's also an important trick. But you cannot do it with OR AA because OR AA is hijacked, which means when you specify OR AA, the opcode does not do what you think it should do. Okay, it is going to do one of the two, either the increment or the decrement. All right, so that means reviewing the labs can also be helpful to prepare for the test. But keep in mind that it is open book and open notes. Okay, so as you study, as you go over this material, if you go like, I probably need a little reminder to myself, in a test to do blah blah blah. Okay, these are all the steps that they need to do. But jot it down and bring that piece of paper with you. Or if you go back to the video recording and go like, oh, this is a nice screen, that contains all the information that I need, freeze that frame, okay, get a little screenshot tool, just crop that portion out, put it onto your own document, print it out, bring it with you. Okay, so most of the work has to do with prep work. Okay, you really have to spend time to prepare for the exam. The more material you prepare, instead of relying on printing out things that I have done, the more familiar you are with the material that you're bringing, and the quicker you can find all that stuff. So that's also important. Make sure you bring your writing instrument, basically a pen or a pencil. Okay, because almost every test somebody is going to ask, does anyone else have a spare pencil? Okay, so make sure you bring enough pencils or pen, okay, just in case one stops working. If you want to bring extra sheets of paper to put your answer, that's fine too. So other than that, I really cannot think of any additional tips to share, at least not today. So maybe on Wednesday I'll remember something else. But you guys can ask questions too. Without any questions regarding the test, on Wednesday we are moving on to the next topic. All right, so I'm gonna pause and end the recording right now. You guys are free to go. You have been free to go for